Here are the top 5 facts you must know about nuclear chemistry for the Regents exam. According to the latest 4 exams, here they are in no particular order. The first one, nuclear reactions release a huge amount of energy per mole of reactant because remember, mass is converted into energy. So this is a fact. You have to know it. Going to number 2, given a nuclear reaction, identify whether it is natural decay, fission, fusion, or artificial transmutation. I'm going to find a Regents question and we'll break it down. So let's take a look at the 4 types of nuclear reactions. Now, you got to go based on pattern recognition, and let's take a look. So this first one here, I'm starting with 2 reactants and I'm ending with 2. This is not natural, this is artificial transmutation. Let's look at natural transmutation, which is over here on the left. You'll notice we're starting with 1 reactant only. The first example, we're getting a helium particle, that's alpha decay. Then this next one is beta decay, and the last one is positron emission or beta positive decay. So only 1 reactant here anytime we're dealing with natural transmutation, also known as radioactivity. The last 2, this one here in the bottom right, I have 2 light nuclei fusing together to form helium, so that is known as fusion. Lots of energy released with a fusion reaction. And the very last one here, I have uranium getting hit with a neutron, which is actually artificial, but look what we're getting. We're getting it splitting into parts with 3 more neutrons coming out. So I'm putting 1 in and I'm getting 3 out. This is the fission reaction. So fission, I have uranium getting hit with 1 neutron and I get 3 neutrons as part of the products. And we're literally splitting it. Here, fusion, we're taking light nuclei and fusing them together. Of course, up here, natural transmutation. Remember, transmutation just means I'm changing the number of protons, which changes the identity of the element. The 3 types of decay you should know, and then artificial transmutation. Don't forget that also on reference table N, uranium-235 is radioactive, and it also will decay naturally, but with a fission reaction, the key is 1 and 3. For number 3, we have reference table N to determine decay modes, and it also gives us half-lives. And there's also table O, which gives us the identity of particles. So let's check that out. So a radioisotope means it's radioactive, and a nuclide means, of course, it's a radioisotope. So these words are used interchangeably. We're given half-life information if we need it. Here it is, the decay mode. And of course, when we're talking about an isotope and whether or not it's radioactive, it has a specific number of neutrons. So don't forget, the mass number means protons plus neutrons. Let's check out reference table O. Reference table O is all about symbols and gives us our notations here. And of course, you know right away when you have a nuclear reaction because you're going to be given the mass number and the atomic number in the equation. The symbol or the notation is typically what you're going to use when it comes to maybe writing out a missing particle for a nuclear reaction. For number 4, we're looking at nuclear reactions and balancing them. You don't balance them the same way you do chemical reactions. For nuclear reactions, we have to make sure the mass numbers are equal on both sides of the arrow and the atomic numbers are equal. Let's take a look at a nuclear reaction. Showing you the example that's the trickiest, and that is that you have beta decay going on here, and we have to watch that -1. The mass numbers are easy. Rubidium starts out at 87. On the other side, we have 0 for the beta particle plus 87 for the mass number for strontium. But for the atomic number, rubidium is 37, the beta particle is -1, and a lot of times students will go with 36, forgetting that there's a minus sign here, but it is 38. 38 minus 1 is equal to 37, just like -1 plus 38 is 37. It's just the mass numbers need to be equal and the atomic numbers need to be equal. And finally, we're up to number 5. Now, I can tell you that I have never seen a Regents test that isn't going to have a half-life question on the test. You have to know how to do half-life problems. There's a couple of different ways that you can approach it. I'm going to do an example here. Also, there's some other nuclear chemistry videos that other teachers have put together. I put together a playlist here on my channel, so you should check those out. But you have to know how to do these. Here is a half-life question that showed up on a Regents exam, and we want to know the fraction of the original sample of radon-222 that remains unchanged after 7.646 days. Now, we weren't given the half-life, which means we need to go to reference table N. So let's do that and bring that back over and answer the question. Go down reference table N. Here it is, radon 222. So it's 3.823. I wrote down the half-life. I like to use T1/2 to represent half-life. Then the total time elapsed is 7.646 days, and I need to know the fraction. You can use one of two different ways. You can use these two I'm going to show you together. That is up to you. Mass and time chart. Now, we weren't given a mass to start with to figure out a mass at the end. Instead, it's talking about the fraction. In other words, we're starting with the number 1, meaning the whole thing. And the time that we're starting is 0. As time goes on and we hit the first half-life of 3.823 days, we have half of the original sample of radon-222. The other half has transformed into a different isotope. So now we're at 1/2. Another 3.823 days goes by for a total of 7.646 days, and we have half of a half, which is 1/4. So it's easy to fill in the table. Just realize as far as mass, we're halving it as we go, and time you're adding. Another way that you could look at this is that the number of half-lives is equal to the total time over T1/2, or the half-life. So 7.646 divided by 3.823 would be 2 half-lives. So we're starting with 1. It's going to go to a half. That's 1 half-life. And then from a half to a quarter, and that is the second half-life. So it checks out either way. Whatever you're more comfortable with is awesome. I'm putting some other teachers' half-life problem solving here on my channel. Check it out. You need to practice. It's going to show up. So this is the top 5 facts for nuclear chem. Keep working hard. Subscribe to my YouTube channel if you haven't already, and good luck.